I am pumped. I went and had some Fritos. Fritos are awesome. They're very, very underrated snack. And I am so energized. I'm ready to go. Okay, here we go. Keep going, crack, throw at. Now, the next problem is a heat problem specifically. We just did a transition problem going from gases, and we were still using gases in the last problem, but we also are talking a little bit about heat. Okay, now, let me talk a little about the joule. The joule is a unit, the International System unit of heat that we need. Heat, work, and heat. Work is how you transfer energy. Heat's a way of transferring energy. These are both energy transfer mechanisms. They're both measured in joules. Okay, joules. Okay, now, the unit, joule, was named after a singer from the 1990s. She had long blonde hair. She had an acoustic guitar and she used to play. That's joule. Okay. Oh, no, that's the wrong joule. Never mind. Anyways, moving on. So the unit joule is not a large unit. You are probably more familiar with calories, the unit calorie. A calorie is a unit of heat. And I am talking about the one for food. Now, there are two different calories for food and calories for chemistry or physics. They're related, not quite exactly the same, but they're very close. In other words, what I mean by that close, and not really close, but what I mean is that a little calorie is, well, let me put it this way. It takes 1,000 little calories, little c calories, to equal one big C calorie. Now, this is the food calorie. So a food calorie is equal to 1,000 little calories. Okay, we'll talk about that in another video when I have to go through what's called specific heat capacity. And let's see if I have to do that. Well, I got to do that in the next video, so I won't do it now. But here's what you need to know. They're both units of energy. This is the food calorie. It takes 1,000 chemistry calories to equal the food calorie. So one food calorie isn't going to get you through very much of the day. You know that's not a lot. So what does that mean? I think 1,000 chemistry calories equal a food calories. That means these are really small. A chemistry calorie is small. And wait for it. It takes 4.19 joules to equal one small chemistry calorie. So what does that mean? That means that the joule is even smaller yet. It's a small unit of energy. But the International System uses the joule. It is small. A lot of times when we're doing thermodynamics, thermochemistry, which is what we're now doing, thermochemistry, then we use kilojoules, because you usually get really big numbers because the unit is a really small unit. All right, a little explanation on that. We'll come back to that in the next video a little bit more. So, this problem here is asking the following. Now, it says enthalpy. Enthalpy, what does that mean? Okay, I have a World of Warcraft character called Enthalpy. Awesome. That's not what it means, but enthalpy means heat transfer of a reaction. So are we talking about heat going into the reaction or heat leaving the reaction? Endothermic versus exothermic. Heat going into a reaction, in other words, heat being a reactant, is going to be endothermic. So if you have A plus B plus heat equaling C, that's endothermic. Heat is going into the reaction, heat being a reactant, endothermic. If heat leaves the reaction, is given off, so A plus B makes C plus heat. Exothermic, heat being given off. Many, and most reactions are exothermic. And there's a reason for that. If you take chemistry 2, we'll get into it, okay? But most reactions by far are exothermic. It makes them more stable. And think about some important exothermic reactions. When you're driving around, you drive here to there. You're using gasoline, combusting. Okay, we learned that, combustion reaction. And that causes heat to be given off. And that heat engine, that's what your engine is in the car, is using that heat. That's really important. So these exothermic reactions, a lot of them, very important. Okay, here's an exothermic reaction. Now, how do I know it's an exothermic reaction? The one I've got written here, which is on here. How do I know that? Because it says, calculate the heat evolved, and that means given off. How much heat is given off when 266 grams of phosphorus is burned in air? Okay, combusts. It's a combustion reaction, not the classical combustion reaction. It's a combustion reaction. We're heating it in oxygen, and we're going to give off heat. So I know that heat's going to be a product. It's going to be a product in this reaction. So let's get rid of this. And I want us to know how much heat. Well, it tells me one other thing that's really important. You can see here the change in H. In enthalpy, the abbreviation is H. Enthalpy is abbreviated by H for heat. Now, some of you might be saying to yourself, well, how come they use Q in the last problem? And we're going to use Q again. So why do you use Q for heat? Well, there are different kinds of heat. And so this heat, enthalpy heat, is an H. Okay. So it wants us to figure out how much heat is given off in this exothermic reaction. And so I'm told that the change in H for this reaction is 3,013 kilojoules per mole of phosphorus being burned. In other words, that's saying is that when phosphorus burns, for every mole that you have, you crank out over 3,000 kilojoules of heat. That's what that's saying. So what do we need to do? If we know it's going to crank out over 3,000 kilojoules per mole, and we want to know how much heat, how much joules, we need to know how many moles. If we know how many moles of phosphorus we have, then we can figure out how much heat we're going to produce. We have to do some stoichiometry. It never goes away. A little stoichiometry here. So let's use this value and figure out how many moles that is. Because once I get how many moles of this phosphorus I have, I'll be able to calculate the amount of heat's been given off because I was given the value per mole. Okay, so grams of phosphorus goes on the bottom. We're going from grams to moles. 1 mole of phosphorus, so I have to add up my 4 phosphori. Phosphori is plural for phosphorus. Yeah, it is. Yes, it is. Check it. All right. Add that up. Phosphorus is 31. 31 times 4. 124. So 124 grams per 1 mole of phosphorus. And if I multiply this through, divide by 124, I'll get how many moles? It's going to be a little bit more than 2. Looks like it's a little bit more than 2. Let's get an answer on that. Exact 266 divided by 124. You kids are doing this at home, right? Should be. All right, in 2.15 moles of phosphorus. Oh, that's the answer to the problem, right? I mean, that's it. We're done. We figured out how many moles of phosphorus. No. We need to know how much heat's being generated in this reaction. So when we combust this phosphorus, the 2.15 moles, how much heat do we get? Well, we were told that we have 3,013 kilojoules per mole. So if I know that I have 2.15 moles of phosphorus being burned, then I get per mole, so it says per mole, 3,013 kilojoules of sweet, sweet heat energy. Multiply that, you get the answer. And that should come out to be 6,463 kilojoules. The moles cancels. Moles is gone. Bye-bye. Bye-bye. And you'll get 6,000, now I forget, 6,463 kilojoules. Now you might be saying to yourself, so what? What's the answer? What's it mean? What's it mean to me? What do I care? What do I care? Oh, and just look at that number. That's kilojoules. So how many joules would that be? 6, 4, 6, 3, 0, 0, 0 joules. 6 million joules. That's a lot. That is a truck ton of joules for just a couple of moles of phosphorus. Just that many grams. It's not very much. It's half a pound. It's a little bit more than half a pound, but it's about half a pound. Not very much. Half a pound to make a lot of energy. Phosphorus is nasty stuff. Nasty bad. Not nasty good. Nasty bad. In fact, in World War II, a little history lesson for you kids. World War II, the United States used to use phosphorus shells and make them explode over German troops. We're so evil. And the reason they did that is because you did not want to be around under those things. So you ran like the wind. Run, Forrest, run.